ready to get engaged, ask lots of questions. Well, from that enthusiastic response, I'm not sure. Okay. Well, so rather than try to introduce, a number of new things in this very last talk, I thought I would try to pull together the and themes from this too. More or less, we're going to go through some review, but then also applying the ideas. Let's see what we can predict on the whiteboard without doing any calculations, for instance. So last time, or the very first time, in fact, I talked about coherent control. Okay? And again, coherent control has some connotation in the field, but really we're just talking about controlling quantum systems utilizing things like interference. Okay? I didn't show this slide last time, but it's sort of a classical picture from the chemistry side of it. So if you take something like OCS, and I'm not a chemist, so I don't remember the name, like carbonyl sulfide or something like that.
I'm not a chemist either.
Anyway, I know we have a few with chemistry backgrounds. Anyway, OCS. Okay, triatomic, it's actually linear. 3 different things, you shine light on it. Now, I write NH bar omega just as this generic pulse that might have lots of photons in it, okay? Might be a strong field. But if you break it up, and of course these are only a few of the multitude of possible final states, you can break this up into 3 different kind of molecular configurations, okay? And that's just if you break it into 2 pieces. You can see that these are all distinguishable. These are different chemical species that you end up with. And at least from a chemist's point of view, if you want to do coherent control systems, you want to control the chemistry, right? You want to make distinguishable, chemically distinguishable final products, for instance. And so one way that folks have gone about this is this kind of pulse shaping genetic algorithm idea. Okay? Now, anybody know what I'm talking about just from that simple description? No? Okay. Well, the idea is that controlling, so the idea would be, for instance, to take this, shine the light on it, and get that instead of the other 2. Okay? Get CS plus O instead of the other 2. How do you do that? Well, okay, you might try to figure out how to preferentially dump energy into that bond. But that doesn't work because you have all these bending things like Phil was talking about. You have all these bending motions, vibrational motions, electronic states. How do you controllably dump it into there? Okay? How can you a priori decide what the pulse is that will accomplish your goal? Okay? People tried that. That's the way they started. And it turns out not to work very well. Okay? So how do you do better? They came up with the idea of taking, say, a broadband pulse, lots of colors in it, and shaping it. In other words, changing polarizations possibly, but certainly the amplitudes of the different colors in the pulse. In other words, changing the spectral phase and spectral amplitudes. That's what the pulse shaper does. Okay? Combining them back, you get this single temporal pulse. You shine it on the system, and you get some outcome. You get some amount of each of these channels. Okay? But maybe that didn't accomplish your goal. Maybe you didn't preferentially make what you want. So you sort of randomly change those around, change those phases and all of those things around. Try again. Did this new pulse work better or worse? If it works better, then you're moving towards your goal. Okay? And this is a multi-dimensional optimization. Okay? And multi-dimensional optimizations are difficult problems to do. So one way that folks came up to do it is what's called, I'm not even sure if the words are on here, but genetic algorithm. This just says algorithm. But genetic algorithm is one of the popular ways to do it. And basically you do the optimization, try to mimic evolution, try to mimic nature. Okay? You define all these different parameters as genes, and you make random mutations, you combine them, and you make children and generations and so on and so forth. I'm sure Wikipedia has a great explanation of it. Anyway, that's the idea. Okay? And it works, it works. I mean, maybe not great, maybe, to be honest, I don't know that much about it. But you can optimize, you can increase your target, okay? This picture on the right is from Silverberg's group. Just shows one example of the kind of pulse that you might end up with, okay? And frankly, this isn't for that system. I don't even know what that was. People use this picture because it's a pretty picture of the kind of pulses you might get out of it. It shows how complicated it might be, and you can see that this even includes polarization changes, okay? So you can take your system, you can shine any system, define what your target is, turn your genetic algorithm and your laser loose on it. I don't know, maybe walk out of the lab, have a coffee, I don't know, whatever you're willing to do with your equipment, leaving it unattended, and come back and have a better answer, presumably, okay? That's one mechanism of one way to go about coherent control. And in a sense, that's agnostic in a way. You don't have to know that much about the system, just turn it loose. You probably have to choose frequencies of your laser that lie in a reasonable range to do something. But otherwise, the system sort of figures itself out, okay? Now, most of us, or many of us on the physics side, like to come from the other approach and maybe come with a more a priori idea, an a priori way to figure out what do I do to control this thing, okay? Because figuring out what the important parts of that aren't always easy, okay? Maybe if you find the right basis, as Phil said, you can extract the important information. What's the important part of this to accomplish your goal? Which is, of course, what some people do also, okay? Just as a review now, what I told you the other day, the way my group is thinking about it, we think of it essentially as a Young's double slit experiment, okay? And I'll just go through this quickly because you guys remember this. I mean, Young's double slit, you get interference over here that gives you the interference fringes. Because you have two pathways that start and end in the same place, you don't know which pathway was followed. Each one has some phase accumulated along the path, so the interference looks like cosine squared of the phase difference, or sine squared of the phase difference, however you want to write it. Okay? I said that in quantum systems, it works more or less the same way. If you want to go from one level to the other, you can control the yield up there, okay, by using 1 photon and 3 photons, okay, and controlling the phase difference between the two pathways. Okay? Now remember, we said we need 3 photons. Why? Parity. Because if we go from, say, what's a ground state, typically say even parity, you absorb 1 photon and that's an odd parity state. You want to get there with 3 photons to also make it end in an odd parity state, the same state, because you need 2 pathways that start and end in the same state, okay, from an observable point of view. So the probability is just the coherent sum of these amplitudes. And of course, you get the interference term, and it's the interference term that we're working with here. We want to control the phase difference between those two. Okay? Now, one thing to notice that in this case, A1 here, which is the amplitude to go along there, is going to depend on the field strength for that photon, for that light field. A2, though, will depend on the field strength cubed. Okay? So, to make a strong contrast here, you need both of these amplitudes, both of these A1 and A2 to have the same magnitude. That's when you get the strongest contrast, right? And so all of these parameters come into the picture when you want to try to decide how to control this, okay? We can do this going to a continuum. So if you start in some bound initial state, absorb photons, you can go to a continuum, and you can control the fragmentation pattern, okay? Because when you go to the continuum, in this case, it's a dissociative continuum. The fragments are falling, the nuclei are falling apart, and you're measuring the nuclei, the heavy particles. Then, if you start in a bound vibrational state, you absorb photons, you can control that fragmentation pattern. Okay? In this case, I'm showing 1 photon and 2 photons, though. So what am I controlling? What control will be possible here? 1 photon, if this is an even parity state, let's say, you absorb 1 photon, so what's the final state there? Odd parity. So if I go 2 photons instead, what's the parity, final parity of the state along that pathway? Even. So I end up with an even parity state and a non-parity state at the same energy. I can control the relative phase between those two, right? I can control the relative phase. What can I control there? Interference, absolutely. But what in an observable way am I controlling if I interfere odd parity with even parity? Symmetry? Okay, but what's symmetry?
The direction.
The direction, okay? The direction. And that's the only way that you can control the direction, is you interfere even and odd parity. Because if you interfere an even parity with an even parity, because if I could replace, well, let's say odd parity with odd parity, replacing this pathway with my 3 photons again, what would I be controlling then? Okay, 1 photon still takes me to an odd state. 3 photons would take me to what? Also an odd state. Can I control the direction now? No. So what am I controlling? What can be controlled? The amplitude. That's the yield, right? How much do you get? That's what you can control. Okay? So identifying, I mean, you're already learning quite a bit with just these simple kinds of arguments, and that's the point I want to get across, that you can make these simple arguments and learn quite a bit. Okay? We'll get more practice, because this is going to be the theme here, is going through this kind of exercise. Okay? And just seeing how much can we extract from these kinds of ideas. Okay? So this is what I showed you the other day for CE phase control. Okay? We started from the Schrodinger equation. This is a Schrodinger equation with a single pulse with a CE phase. Okay? The total wave function here, I've indicated the C phase as a parametric dependence. I told you that because this Hamiltonian is periodic in the C phase, we can expand this total wave function, all the C phase dependence, with the Fourier series. Okay? Again, this is just what we talked about the very first time, during my very first lecture. In this case, this is exact. There's no approximations. You substitute this into that Schrodinger equation, and you get this set of coupled equations. They're coupled because n takes on all values. Okay? Minus infinity to plus infinity. So what this equation is saying is that this phi n is coupled to phi n plus 1 and n minus 1. Well, that's just saying we have photons, we have the dipole approximation. So if I have 3 photons, the dipole operator is going to couple it to 4 photons and to 2 photons, which of course makes perfect sense, right? Because this dipole operator, that's in a sense how we define a photon. When that dipole operator acts once, that's a photon. That's what we say in perturbation theory, right? Okay, so this phi n state couples through this dipole operator with the neighboring photon states. And this n, and that was the point that I discussed last time, that n can be thought of as telling you the number of photons for that particular channel. Now, keep in mind, photons is a very fuzzy sort of thing, right? It's not, we aren't quantizing an electromagnetic field, it's nothing like that. Photons are something that have, on average, h bar omega of energy. But that's it. Because we're in the dipole approximation, they don't even have momentum anymore, right? And the dipole approximation, the wavelength is so long, that's the assumption, right? The wavelength's really long. It doesn't even have momentum. All it has is energy. Okay? So a photon, in what I'm saying here, is something that just has h bar omega of energy. Now, it doesn't have exactly h bar omega of energy because it's a pulse. So it has some bandwidth. So this h bar omega, the omega you should think of as the carrier or some kind of a central frequency. But it's really kind of a fuzzy thing. So photon is shorthand, okay? It's just easy language. But these phi n's tell us about the amplitude to absorb n of these photons, okay? As I said last time, the nice thing about this expression is that these phi n's are now independent of CE phase. So I only have to solve this equation once, and I can get all the CE phase dependence. Now, solving this equation once isn't necessarily an easy thing to do, but conceptually, that's the point. Okay? So the CE phase dependence is all right there, which means I have the exact wave function and the exact CE phase dependence, written out. So I can derive the CE phase dependence of any observable. Again, that's an exercise we did last time. This equation, maybe it applies to, I don't know, what was the molecule? You had some molecule with like 12 nuclei, CH3OONOC.
See, I'm not a chemist. Right.
Anyway, it applies to that molecule. Because this H naught, I don't say what that is. This doesn't specify what that is. This H naught could be anything. It could be the table. You want the CE phase dependence of ionization of the table? Okay. Well, there's a few more complications if you want to use the table, but you get the idea. Okay? It applies to any system. And to me, that's part of the strength, because I can use this as a conceptual picture to try to predict what will happen even in more complicated systems. And I added this last point that we make measurements. When you make measurements, it's in the spectral domain. Okay? If you're measuring fragments, the particle fragments, electrons, protons, heavy particles, all the fragments from one of these processes, you're measuring their momentum or their energy. That's in the spectral domain. So I find some advantages of thinking in the spectral domain. That's what going to the photon picture does. So Phil talked about going halfway in between. I'm going all the way to the frequency domain. Okay, let's see what we can get with that. Now, a thing to keep in mind is no one of these pictures is perfect for everything, right? I'll try to sell my idea, just like every one of you, when you get up, will try to sell your own ideas, okay? But it's good to know more than one point of view. That's one way to get more insight, okay? So, last time we talked about the spatial asymmetry. This time, I want to go through the yield argument a little bit more, because that will have an impact on what we'll talk about. If you use this expansion, and you just calculate the total yield, so the energy differential probability in this case. We have pulses, so we define probabilities, not rates, things like that. Okay? You can write this down explicitly, okay, where these psi n's or the phi n's are those photon amplitudes. The E and the O, remember, indicate the even or odd parity. Okay? And so here's the CE phase dependence. So the total yield as a function of energy, because each of these things will depend on energy through the K. Okay? Is the sum over all of these n's with these amplitudes. And of course, this is just an integral over angles. Okay? So if you want CE phase dependence, you need n to be different than n prime. And you need this amplitude and this amplitude to both be non-zero at the same K, right? Because you have to start in the same initial state. That's taken care of in these, because these are the time-dependent wave functions. They started from the same initial state. But you need to get to the same final state. And that's what the analysis is telling us about. Are we getting to the state with the same direction finally? Okay? So the two pathways that interfere, this is the amplitude for one, this is the amplitude for the other. Actually, I should say this is the complex amplitude for one pathway. This is the complex amplitude for the other pathway. And what it says is you have to have even interfering with even and odd interfering with odd, which is what we just said a second ago. If I want to control the yield in this sort of a picture, I need 1 photon and 3 photons. That's how I control the yield. Okay? So, you get even interfering with even, or odd with odd. You get the same parity interfering with itself, only when n and n prime differ by an even number. 0, 2, 4, minus 2, minus 4, and so on. Okay? But that also tells you immediately, and I'm kind of skipping ahead in my bullet points, so let me maybe follow it, because I can't change my clicker order that easily. these amplitudes interfering lead to this sort of pictorial picture. This sort of pictorial picture, I like that. This sort of picture. It's turning this one on the side. So instead of energy going vertically, energy goes horizontally now. This is the initial balance state, and I'm absorbing some number of photons. Okay? You can think of this red curve as the absolute square of one of these amplitudes. Okay? Because this is for a fixed number of photons, in this case 3 photons. So that would be n equals 3, it would be an odd parity contribution. And it, like I say, it's the absolute square of this. So this is the absolute square of one of those amplitudes, another, another, another. This is for 3 photons, 4, 5, 6. Okay? We said that we need to get C phase effects here, we need these amplitudes to contribute at the same momentum or the same energy. So we need to look at the overlap here, right? So which overlap am I looking at? Am I looking here? No. Because this overlap is between 3 photons and 4 photons. We just got through saying we need the number of photons to differ by 2. Okay? So in fact, we're looking at the overlap between this red one and the next red one. See how big that is in there? So this one, this particular example would show no control on the yield. Okay? You get control on the yield only if you make the pulses, the bandwidth of these things broader. Okay? So that there's overlap in there. So that overlap region is between neighboring photons. Those are different parities. So what control would that be? Direction. Okay? To get control on the yield, you need interference between things with the same parity. So that's those little boxes. Okay? So you're way off in the tail of your power spectrum of your laser pulse. Okay? So you need, in transform limited pulses, you need quite short pulses. And as I said, this is just a Fourier series finally, right? This is a Fourier series in phi. And it's going to have terms 1, cosine 2 phi, sine 2 phi, but also cosine 4 phi, sine 4 phi, 6 phi, and all the even frequencies. Okay? So in principle, you can use this knowledge now to economize your calculations. I mean, if you know you only need, if you're at relatively low intensities, such that you at most expect interference between, say, 3 and 5, or 4 and 6, or things that differ by only 2 photons, then how many C phase points should you calculate to reproduce cosine 2 phi, sine 2 phi dependence? Do I need 20? 4? Well, let's just think of the Fourier series. If I do a Fourier series, I have 1 coefficient there, 1 coefficient there, and 1 coefficient there. So I need 3 parameters. Okay? So at least if you're going to just fit, 3 C phases would be enough. Now, of course, there's a whole theory, Nyquist theorem, and all of that you can use to do this in a more rigorous way. But most people, when they do calculations for C phase effects, they're going to calculate 20 or 30 C phase points. Okay? If you know that at low intensities, this is your dependence, you can greatly economize on those calculations. Okay? Similarly for if you're doing spatial asymmetry or other things. Okay? Because you can fill in, once you have those 3 points, you can use this Fourier series to get the whole curve, to get the whole dependence. Okay? Is that clear? Other questions?
What phi k do you use here? I mean, so each of these peaks is a...
What is this?
Yeah.
Okay. This guy is an exact scattering state for the system. Okay? It's a scattering state constructed, it's a 3D thing, right? It's an exact scattering state constructed so that finally, at long times, it has good momentum going out in this direction. It looks like a plane wave asymptotically in this direction, because that's what you're measuring. You're measuring the momentum asymptotically. So if you want to really correctly calculate a momentum distribution, you project onto the scattering states of the system set up this way. Okay? Other questions? Well, so should we do an example? Should we see, let's say we don't know anything about ATI spectra for atomic ionization. Can we predict the C phase dependence and the C phase effects on an ATI spectrum? Well, so I put up a few questions. What C phase effects do we expect in single ionization? Okay. Can we anticipate? What is the best observable for C phase effects? So for instance, if, what should you look at first? If you aren't sure whether you have good control or short enough pulses or any of those things, what's the thing that's most likely, what observable is most likely to show C phase effects? And finally, this is a question that Ken raised the other day. Can there be C phase effects in double ionization but not in single ionization? Okay, he was talking about looking at this non-sequential double ionization and the calculations he was doing. Okay, so where do you start? Where would you start to answer this question? Again, I'm trying to use the framework that I presented here, right? Where would you start? Huh? Start from the first question. Very good. We'll start with the first one. What C phase effects do we expect in single ionization? And I'll be more specific. We'll say the ATI spectrum. Okay? Just the photoelectron energy spectrum, not a momentum distribution or anything like that. Just the energy spectrum. Well, okay. So I would imagine we might want to draw a picture with energy. Now, so I don't know. Maybe something with the bound state energy here. Kind of looking at the picture I drew up there, right? Okay, so you absorb some number of photons, and of course in an atom, most likely it's a lot more than this if you're using something like 800 nanometers, right? Okay, so we might expect one peak centered there, right? Okay, so there will be another photon, another peak centered there. Right, and let's just take it concrete and simple. Hydrogen plus a strong field gives us proton plus electron. Okay, and we're measuring the electron. So one more photon. Now, drawing these kinds of pictures, drawing these nice peaks, how am I deciding what the width of this is? What's the width of one of those peaks? What's it depend on? The bandwidth of the pulse. Okay, in first order perturbation theory, this profile is exactly the bandwidth, the power spectrum of the laser pulse times the dipole matrix element. Okay? Multiphoton is kind of like that. Okay? It's a good way to think, especially when lowest order perturbation theory applies. In other words, if you're approaching this from low intensities, you take the lowest order of perturbation theory that works. This is kind of what the pictures look like. Okay? As you crank up the intensity, these things are going to get twisted and distorted and shifted. Okay? So we're coming up from low intensities. So lowest order perturbation theory is what we're talking about. So how do you expect the peaks of these to fall off? Because this is 3 photon. This is 4. This is 5. How would you expect the peaks to fall off? Yeah, so perturbation theory would be the argument. So what does perturbation theory say? Probably for the nth peak, scales like what? Intensity to the n. Okay? So this would fall off like a pocket like this. Okay? I haven't drawn it exactly that way. What's it say about the width of these peaks? They get narrower? Okay, I'm hesitating, so. Who says narrower? Good. Who says wider? Who says no change? You would expect that they get broader. Okay? And the idea is this. If you were to take That's after, say, 1 photon absorption. Okay? And this is a very simple argument. Okay? This would be still the energy axis. After 1 photon absorption, you can imagine 2 photon is starting from this level. So you would go with a photon like that, right? Except that has some distribution too, because there's some bandwidth for that photon. You go from up here, there's some bandwidth for that photon. You go from over here, there's some bandwidth for that one. Okay? So the total peak over here would be the sum of all of those. Okay? And again, this neglects interference effects and perturbation theory and you know, all complications like that. The dipole, like I said, it's a very simple argument. This peak then, the sum of all of those, ends up being the convolution of this peak, if it's n photon, with the laser bandwidth, the power spectrum, which means that the width and frequency, or in energy, of the n peak goes like square root of n if they're Gaussians, of the original. Okay? So they get a little bit broader, and again, that very simple picture. So as you go higher, these will get slightly broader. Okay? What else could we say? Well, we want to look for C phase effects, right? So we're going to have more and more peaks out here. They might get a little bit wider, still be spaced by 1 photon. Okay? Where would you look for C phase effects? What C phase effect would you look for first in this spectrum?
Between different parities.
Between different parities. So this would be odd and this would be even, right? So these would be opposite parities. And so the overlap there would certainly show a C phase effect. Would it show it in the spectrum? This is the energy spectrum, right? Which means it's the yield. So the interference of different parities gives us control over what? Direction. So there will be C phase effects in here, but you would have to look at, say, the momentum distribution to see it. Okay? But that would tell you what energies to look at. Okay? But if so this would be in the direction. Okay? And of course it would be in all of these spots.
Do you see more at higher photon numbers?
And as long as this kind of an idea holds at least, and these get broader, then the overlap would get bigger, so yeah, you would expect to see bigger effects at higher photon numbers. Okay? What else? How would we see C phase effects, or where would we see C phase effects in this picture, if they were there? Again, this is the yield, right? So which parities interfere? The same. So it would have to be this guy with this guy, right? So it would be the overlap of those two, which I didn't even draw in here because they're so narrow. Okay? We would have to get to much broader pulses. Again, it's the same picture I drew, which is exactly the point. It doesn't matter what the system is. It could be nuclei and H2+, it could be electrons and ionization. Okay? Well, we would need to go to broader pulses such that we had, something like that. This guy would, overlap like that. Okay? Now, this says that we're saying this is roughly the bandwidth, so the full width half max of this power spectrum has to be comparable to a photon, right? So delta omega, approximately omega, can we actually do that? And transform limited pulses? How long is that pulse in time? Do you have any idea? Okay, so for Gaussians, and for most transform limited pulses, delta omega, maybe I should write this down. Delta omega, the bandwidth, over the photon is approximately, let's see, 1 over the number of cycles, up to a constant. I think for Gaussians, the constant's like 0.3 or something. Okay? So if you have pulse that's one cycle long, roughly the bandwidth is going to be on the same order as the photon energy. Okay? And that's about as short as you're going to get. That's about one cycle. Okay? Again, up to factors of 0.3 or so. So getting things this broad, at least in a transform limited sense, will be a bit of a challenge. Okay? Again, unless we go to high photon numbers and things broaden, then you might see more yield control out of larger photon energies. Or larger photon numbers, I should say. Okay? So, what C phase effects do we expect in synchronization, at least from this picture? Control, of course it depends on the pulse, right? But you can control direction and you know where to look for in energies. Again, as we come from low intensities. Okay? You know where to look and what to do to try to get control over the yields. But notice also, the control over the yield, where these overlap, is going to lie under one of your peaks. So it's going to be a modulation on a big signal. This directional control is a modulation on a small signal. So both have their challenges. Okay? What else? If we wanted to see anything besides the lowest order interference, we want to see, cosine phi in the direction is just these two interference. But in principle, 3 can interfere with 6 over here. Right? That would give you a delta n of 3. That would give you a frequency of 3. So you would see cosine 3 phi contributions in the C phase dependence. Okay? But then this would happen over that. That's a huge bandwidth, right? Or a really tiny effect. You could look for delta n of 4, frequencies of 4 for yields. That would be, say, 3 interfering with 7 over here. And you can see how unlikely those are. That's why all measurements today on C phase effects and asymmetry just look like cosine phi. Almost all measurements in yield just look like cosine 2 phi. Okay? Because getting to this other regime is really, really hard. Okay? So, again, in this kind of a picture, we have some answer to the first question. When the intensity goes higher, the picture gets more complicated because these peaks aren't quite as simple as this lowest order perturbation theory predicts. However, there's nothing wrong with the formulation, only in the way we draw our simple picture for it. Okay, see, phase effects, even at high intensities, are still interference between, say, n and n plus 1 photons, or n and n plus 2 if you're looking at the yield. Okay, you would just have to have the corresponding picture, and it's hard to write that down a priori. Okay, but it doesn't change the fact that you would expect to see cosine phi for the asymmetry. Because that's just a simple outcome of all of this. Doesn't change the fact that you would expect to see cosine 2 phi for the yields. Okay? So what do you think? Having that discussion, what do you think, what observable would you look at first if you want to see C phase effects? Direction? Why direction? It's the lowest order, right? Because it's these guys interfering rather than those guys interfering. So yeah, one would expect to see directional effects before you see other effects. And in fact, that's what people have seen. They saw directional effects. There's many more measurements on directional effects than on yield effects. Which effect do you think is more interesting for the coherent control, say controlling chemical reactions? The yield. Okay? So if you were going to start out and you wanted to control the yield, would you pick C phase as your parameter to do it? I mean, at least to me, I'm not an experimentalist, but that looks like kind of a hard way to go. Okay. How about that last one? Can there be C phase effects in double ionization but not in single ionization? This connects with the picture I drew last time. So instead of this kind of a picture, we really need, well, this is a picture for single ionization. Keep it in your mind because I want to draw the one for double. And I want to draw it high enough for everybody to see. So if you're going to do double ionization, remember we had this kind of picture, energy for electron 1, energy for electron 2. And in this case, you're going to get the multi-photon piece will look something like that. And again, I'm just sketching here. So this line is total energy, and this might be, say, n equals 3, n equals 4, n equals 5. Okay. So if you wanted to see CE phase effects in a direction, and it depends on what system we're looking at, whether that's possible, where would you look for them? What's that? Asymmetry, yeah, but where, do you have any guidance where you would look? What energies would you look at? In between, right? Because even in double ionization, if I absorb 3 photons, every photon changes the parity. I don't care how many fragments there are. Triple ionization, double ionization, triple dissociate, doesn't matter. Okay, you absorb a photon, you change the total parity. Okay, so if you want to change the directionality, if you want to control the directionality, this would be odd parity, for instance, even parity, odd parity. If you superpose even and odd parity, that gives you control over directionality. That's in this region, right? Or this one, or the next one, or the next one. So those would be the energies you would look at. Okay? So if you could make cuts here and focus on those parts. Okay. Could you see those directional effects before you see them in single ionization, do you think? I mean, if I were to draw an energy scale, and let's say here's my ground state, and I won't say 0 energy. And I'm going to need 2 thresholds. I'm going to need single ionization threshold and a double ionization threshold. So I would have 2 lines here. So should the single ionization threshold be above or below double? Below. So single ionization is here, double might be over there. Which one takes more photons to get to? Double. And again, if there's something to this argument, then the more photons you absorb, the wider the peaks get, right? So do you suppose there might be a possibility for CE phase effects in double ionization before single? Again, now with some caveats. You know, that simple picture has to apply. You have to be low enough intensities. So for the whole picture to sort of work in the simple way that I draw. Okay. But we haven't, have we used anything for a specific system? I didn't even tell you what system I was talking about. Okay? So that's, again, to me, that's the advantage. You can make arguments based on dipole selection rules, symmetries, energies, things like that. Yeah?
So, of course, atoms have this parity, and diatomic molecules, but
All molecules have it.
really,
Every system that interacts by pairwise central forces has eigenstates of parity.
CL?
Yes, absolutely. Every molecule, every system that interacts through pairwise central forces has eigenstates of parity. So, you know, when people talk about, I mean, this is a common misconception that molecules have permanent dipole moments. They do not, unless there's an external field. Then the external field mixes eigenstates of different parity that are close together, form a Stark state. That's how you get the dipole. That's how you see dipoles. Okay? So they have eigenstates of parity. Now, they may not always be the most convenient basis. I'll grant you that. Okay? But guaranteed they have it. Okay? If you have any molecule you want to pick, put it in the universe with nothing else, no external fields, nothing else, eigenstates of parity. This is it's a pretty simple proof, because if you can show that the parity operator commutes with the Hamiltonian for any system with only pairwise central forces. Okay? Yeah.
So I follow and agree with these arguments you presented, but it seems like competing ionization pathways for double ionization would really make this hard to see.
What do you mean? What other kind of pathway do you mean?
Well, I suppose I guess it depends on the pulse, but which, for instance, which electrons ionize first or...
It doesn't matter. It absolutely doesn't matter. That's the point. The intermediate states don't matter, right? Because you have a system, you have initial state, you have final state, some number of photons get you from one to the other. The intermediate states don't matter. So this would assume that you state resolve. So if you double ionize but you leave a core behind, right? Then you make this picture for each core state left behind. Okay? If you had a different core state left behind, you would have a similar picture, but it would be shifted. Okay? And that would be complicated. So using this depends on a state selectivity that you may not have an experiment, but you can use this to use this kind of idea to make a prediction for each core state, and then imagine what their superposition would look like. Okay? Do you have questions?
You mentioned pairwise,
Yes. What's that? Pairwise interactions. Central interactions. Coulomb interaction. Right? The Coulomb interaction, which describes all our molecules, only depends on the distance between the particles. So that's a two-body central force. Okay? And you can see then why parity commutes with it, because if you change all those vectors to their minus, then those magnitudes don't change, right? Okay. So maybe you're getting the idea a little bit better. Are there any questions? Another question. Okay.
so you have a C phase.
Yeah.
I mean, different C phases give you different peak intensity for a single pulse.
No, the peak intensity is the same because you have the same envelope.
But I
You can think about the instantaneous field maybe being different, but intensity is a time average quantity, right?
but the atoms stay the field. How that happens.
They do. I can show you the equation. There. Right? This is exact. And that's just the envelope. So the atoms see the field or the envelope? What's more important?
But the atom is not real.
It's not? Can I write the field as a carrier envelope in the carrier envelope representation?
Yes.
Yes. Okay. But again, see, the point is, all these are exact steps, right? No mathematical question there. This is carrier envelope, and it's the envelope that matters in this equation. You get all the C phase dependence, which means moving that peak field underneath that envelope. You get that information from this superposition. Okay? And that's the point here, is we're in the spectral domain, not the time domain. So there are no fields anymore. We don't talk about the instantaneous field in this picture. Okay? We're talking about the spectral content. Okay? We're talking about the spectrum. So it's a very different picture than most people think of C phase effects. And as I showed you last time, you can make predictions here that you wouldn't make if you were only thinking of the field. Okay? And I don't have the picture here, but I showed you last time. I posed the question, what's more important for seeing C phase effects? Is it the pulse duration, or is it the bandwidth of the laser pulse? Well, again, if we have, maybe I'll use it here. Did I really say anything about pulse duration in this picture? No, only in the sense that I sort of gave you the idea that these are transform limited pulses. But if they aren't transform limited, then I'm not saying anything about the pulse length in these pictures. Okay? What I'm saying is What's the spectral content? What's the power spectrum? And so to see CE phase effects, you just need the power spectrum of the pulses to overlap. The power spectrum, sorry, the spectral peaks to overlap. So you need the power spectrum to be broad enough. And I showed you numerical examples that supported that. I showed you experimental examples that supported that. Okay? So that, we did, my experimental colleagues in ITAMP group at K-State, they chirped something with 5 femtosecond transform limited pulse out to 20 femtoseconds. Okay? 20 femtoseconds is, well, 2.5 femtosecond cycles is how many cycles? Quite a few. And they still saw C phase effects. Okay? Which, in most, if you're thinking in terms of just the field, you would not expect that. Okay? So yeah, you've identified exactly the key difference between this picture and the way people normally think about this. Yeah.
So I didn't understand why even an atom is possible for every system, because if you have molecule with two center and you look at the ionization, you have one electron with two center, there are no central.
No, this is the total parity of the system. It's not the parity of just the electron, it's the total parity of the system. That's what has to change when you absorb a photon, is the total parity of the system. Okay? You can break it down if you want. You can take that further and talk about if you have symmetry quantum numbers for the electronic part alone, how those would change under a dipole. But that's not the parity that really changes when you absorb a photon, it's the total parity of the system. Okay? And every molecule is, the Hamiltonian is just a sum of the electron-nuclear interactions and the electron-electron interactions and the nuclear-nuclear Coulomb interactions, all central forces. So parity eigenstates. Okay? But I mean, you can get into those details. I mean, in a sense, from this point of view, those are details. Okay?
Well, I'm just wondering if they
Yeah.
are, because let's take the ground state of the system. That, Start easy with the ground state of hydrogen.
Okay. Hydrogen atom even.
Hydrogen atom, right?
Okay.
That's what I meant.
Yes.
Okay. What would you say is the parity eigenvalue of that system?
It's even parity.
You didn't even hesitate.
Yes.
Now, let's take something that's a little bit more complicated. Choose your molecule. I mean, I would choose the diatomic with the two nuclei are not the same.
Okay.
CO.
CO.
It's
Okay.
still, it's still, by the way, it's still closed shell.
Sure.
Okay. Even though ground state parity is what?
Ground state of the system?
Yeah, ground state, in the ground state, what's the parity?
To be honest, I don't know in that
Yeah.
case. It's even or odd.
Exactly. Exactly. In other words, it has two degenerate ground states, even or odd. So.
No, I don't think so.
Is that right?
I don't think so. Once you include all the nuclear pieces, I don't think that's true. I don't think that's true. Now, they might be close. I would be very surprised if they're exactly degenerate. The electronic part, yeah, I mean, if you have pi states, for instance, or something like that, yeah.
Also, in many value system, there are no even and odd. It's so that you can have three even and
True.
so
Well, is that true?
sometimes
Yeah, probably. Yeah.
sometimes you cannot use this argument.
Oh, but you can, because, you know, you have the even parity states, you have the odd parity states, you absorb a photon, you go, every time you absorb a photon, and that's what I'm drawing, you have to change parity. I don't care what the states of the system, if they're accessible or not, that's the dipole part, right? If there's no dipole to get to this one, maybe this one is suppressed, right? But this is one photon, that's another photon, just by energy. Then guaranteed, this is one parity, that's the next parity, that's another parity. Now, there's a complication of molecules that hasn't been mentioned, and that is molecules usually come in a thermal distribution. Okay? The thermal distribution doesn't care about parity, it only cares about energies. So your CO example might be, the ground state might be even, and then first excited odd and so on. But it's going to come in an incoherent superposition of those, a thermal distribution of those determined by the temperature. Okay? And all of that will come in here, but I can use these arguments to argue what happens with that even parity ground state, with the odd parity excited state, and then think about taking the thermal average of the outcome. Okay?
I think it is safe to say that there are no molecules we know which spontaneously break symmetry. In other words, exist in a superposition in the ground state, in the superposition of odd and even parity states.
In the total parity, look, I'm not a molecular physicist either, so I certainly can't say that. I'm just saying from a fundamental point of
I
view.
think this is safe to say.
However, in ground states, many of them have even and odd parity states close enough that even small external fields, the environment of a liquid, makes them polar. That means that they have a dipole. That means that you've superposed even and odd parity states. Because what happens when you superimpose even and odd parity? You get directionality, right? Just like we talked about. And that a dipole is directionality. So, yeah. Other questions? Do we have time for more questions?
Well, you're the last speaker, you have as much time.
That's true. We have lunch, right?
I don't know when the lunch is served, but we have time.
Okay. Well, I wanted to make at least one more point. Well, tell me when I should stop. That was the other point I wanted to make. I realize actually I have 2 points I want to make. It'll be 3 in a second. Just hold on. So, as I told you, we can write these observables. In this case, I just wrote the momentum distribution. It's a Fourier series, so I just rearranged the series I showed you before so that the C phase dependence is clearly in a Fourier series form. So this whole quantity will give you the amplitude of that Fourier component. But that means I can take an experimental spectrum like these, which were taken again by my experimental colleagues at K-State in the physics group. Okay, I should write down what this is so it's clear. So this particular experiment is H2 plus a strong field goes to H plus H star plus, no, that's right, just H plus H star. Okay? Okay? And so what's measured here is the asymmetry of those, because H star, an excited state of H, is distinguishable from H. So you can measure the relative momentum distribution of those, and you can look at their asymmetry, the probability up and the probability down. So this picture is shows the density plot of this asymmetry, normalized asymmetry, as a function of C phase. So that's the C phase divided by pi, so this is up to 4 pi here. This axis is the kinetic energy release, the relative energy of those two fragments. Okay, and you can see that there's, the scale up here for the normalized asymmetry is minus 0.2 to 0.2. And you can see there's clear directionality changes as you change the C phase. Okay? But I told you, this is a Fourier series, so you can take the Fourier transform of that. Go to n space, okay, or delta n space. So, what you see, again, this is KER, so they did this for every KER slice. You see this strong line at 1 phi. Okay? That means it's delta n of 1 or minus 1. So that's a cosine phi contribution to the asymmetry. That's what we said would be the dominant one, right? That's the interference between neighboring photon peaks. Okay? But you also see some noise, but you also see this fairly strong peak over here at delta n of 3. That's the interference of pathways that differ by 3 photons in their absorption. Okay? And if you look at this inset here, that's a cut. Let's see, I have to get close to read this. That one is, you can see maybe 2 lines right here. That's this peak, right? That's this peak. So if you just take and bin along there, you can see that's the trace. That's the C phase dependence along this way. Clearly not cosine phi. There's a clear higher frequency